Here we go again, section 5 now. Energy is a word that pops up a lot of places. Energy means the ability to do work, or that's one way of defining it anyhow. And so I guess the logical place to start is with the meaning of the word work. Work, if you're going to be kind of imprecise about it, means force times, well, simple example. You got somebody pulling a wagon down the driveway, and how hard do you pull it times how far do you pull it? That's the amount of work you do. Force is a vector, displacement is a vector, which leads us into the need to multiply a vector times another vector. I did some vector arithmetic earlier in the course. I talked about a vector plus a vector and a vector minus a vector and even a vector times a scalar, but I said a vector times another vector was going to have to wait until another day. Well, it is now another day. So there are actually two distinct operations. I should aim that a little higher. Closer. Okay, so now that I'm done messing around with the camera. Section 5. Work. Force times displacement, which means we've gotten into a situation where we need to multiply a vector times another vector. As I started to say, that says multiplication, by the way, for those of you who are cursive challenged. As I started to say before I got distracted by the camera, there are two distinct operations you can do with vectors that are kind of analogous to multiplication of regular numbers. There is, well, it's not the formal name for it, but what everybody calls the dot product. Let's say that's vector A, and let's say that's vector B. And vectors once again have this parallel displacement property, which means I can slide them around the page anywhere I want to put them. Well, this time I want to put them together so that they're with their tails together like that, so that they form an angle theta. And A dot B equals the magnitude of vector A times the magnitude of vector B times the cosine of that angle that they make when you stick them together. Or at least that's how you would find the dot product from their magnitudes and the difference in their directions. Now, as I've said before, there's also, you've got your choice, two different ways of describing vectors, with magnitude and direction, or with components. And if you want to find the dot product from the components of these vectors, instead of the magnitudes in that angle, then that goes like this. multiply the x's together, multiply the y's together, multiply the z's together, and then add them all up. Work is a dot product, okay? The other way of multiplying a vector I will leave for yet another day, probably about 2 weeks from now, if I remember right. Cross product. Again, not really its formal official name, but it's what everybody calls it. The dot product gives you a scalar, okay? These are all numbers, magnitude, magnitude, cosine, 3 numbers to multiply together, or same thing with the components. You just multiply and then add and you get a number. With the cross product, A cross B gives you another vector. So vector times vector gives you scalar, vector times vector gives you another vector. The details on the cross product are, I believe, in section 7. So work W for work, not to be confused with W for weight. From here on out, I'm going to try and use mg for weight, so I don't have 2 different W's floating around right next to each other. Force vector dotted with the displacement vector. Up until now, there's a slight change of notation here. Up until now, I've used delta x for the displacement, or if something was going in the y direction, delta y. Well, I want something a little more general than that. Something could be moving along the arc of a circle. How many meters did it move along that curve? So I don't want to use delta x because that kind of implies you're going along the x-axis. So S, why not? But it's newtons times meters, okay? Now, based on this definition for the dot product back over here, what that means is magnitude of the one vector times the magnitude of the other vector. Actually, let's rearrange the order a little bit. Magnitude of the one vector times the magnitude of the other vector times the cosine of the angle between them. If you are, like in this first example that's coming up in a couple minutes, where somebody's pulling a wagon, well, the front of the wagon's down there and your hand is up here, so the handle makes an angle. If you have a force in that direction, and the wagon is being displaced in that direction, what F cosine theta is F cosine theta is the component of the force along the displacement. So the thinking behind it goes like this, okay? Well, sort of begin at the beginning. Just in common everyday usage, if you move this little wagon 10 feet, pretty much everybody would agree, that's less work than taking it a mile, okay? More distance, more work. Also, I think everybody would agree that moving a wagon 10 feet is less work than moving a refrigerator 10 feet. Larger force means more work, all else being equal. So how hard did you have to pull or push times how far did you push it, and that's the work. But a little detail. So you're pulling this wagon along the driveway, and you've got this friend, really nice person, not so bright, comes along, decides to help. So as you're pulling the wagon down the driveway, they decide to press directly downward on the wagon, okay? Now, by the time you get where you're going, your friend might be just as tired out as you are, but they didn't really help move the wagon, okay? Forces across the direction of motion are not thought of as doing any work. Only forces along the direction of motion do work. If you have a force that's at an angle, well, as we've already seen, that force at an angle is equivalent to two other forces acting together, called its components, one along the direction of motion, one across the direction of motion. This component across the direction of motion is like our well-intentioned friend I was just talking about. It doesn't actually accomplish anything in terms of moving the wagon, propelling it along. So only the component of the force parallel to the displacement is thought of as doing work. And F cosine theta is that parallel component. This thing about the dot product is just a shorthand way of, and this is not the only situation where two vectors and the cosine between them kind of go together. So it's a common enough situation that they came up with a sort of a shorthand notation to mean this sort of thing, and that's what the dot product is. One more little detail I should probably mention. We aren't going to get into this very much in this course. It's something I'll have to mention occasionally now and then. It's nothing you're going to have to actually do yourselves until the spring semester when you're further along in your math course. But what if the force is not constant? For example, I believe it's section 10 in here. We're looking at forces from springs, or it doesn't have to be a spring, any kind of elastic force, like from a rubber band or whatever. The farther you stretch the spring, the harder it pulls, okay? So if I had one end of a spring attached to the wall over here, kind of a long spring, if I had the other end attached to a block sitting over here on the table, and then I let go of the block, well, as the block slides along the table, the spring gets less and less stretched, which means the force from the spring gets smaller and smaller. The force from a spring increases the amount you stretch it and decreases the closer it gets to its equilibrium length. So how would you calculate the work done by that spring on this block that it's pulling across the table? Work is force times distance, but what do you do for the force when the force is continuously changing from one point to the next? Well, you could get an approximation for the amount of work done. Here, there's the wall, there's the table, There's this block I was talking about. There's a very stretched out looking spring. And the block is going to go from there. It starts out there and it's going to end up there. There's the displacement S. Well, to get at least an approximation for the work, you could take that entire displacement and divide it up into lots of little pieces. Each of these pieces represents a relatively small change in the length of the spring, so the force doesn't change much. You could use that more or less constant force times this much distance to calculate the work done in that part of the overall displacement. Same thing here. The force when the block is there times this short distance, and do that for each little increment, and then add up the work in each little piece to get the total. That would give you a good approximation to the work that's done. But of course, the force still changes a little bit, even over a short distance like that. To improve the approximation, you can use a larger number of smaller intervals, because that gives the force even less of a chance to change over such a small interval. To make the approximation exact, what you do is you take the limit of infinitely many, infinitely small intervals, okay? You make the number of subdivisions approach infinity, which means that the width of each one approaches 0. Add up the work done in, how much work does it total up to in that limit? And this is the basic idea of integral calculus, okay? Calculus, I mean, there's a lot of details, but as far as basic ideas, calculus is basically about two things, derivatives and integrals. So the general definition of work that would apply no matter what's going on, whether the force is constant or not, looks like this. Work is integral F dot ds, which may not mean any, focus, come back, okay, may not mean anything to you right now, but you know, if it gets to be around Christmas time and you look at your notes again, you'll go, oh, that's what he was talking about. So anyhow, a little bit of background information. This would be the general definition. I wrote here, if the force is not constant, with the idea that if the force is constant, you use this version back over here. But actually, I suppose it would have been more accurate if I said that's the definition of work if the force is constant or not. Because if the force is constant, constant can be taken out from the integral of ds is just s. This reduces down to that when the force is constant. But, well, that's just background information. For purposes of this course anyhow, this will, for anything you have to do yourselves, this will be the definition of work, okay? I may occasionally mention this sort of thing, like when we get to section 10 and I'm talking about springs, but. So work is a scalar. Remember I said earlier, the dot product is a scalar. You should be glad to hear this. You've probably noticed that vector arithmetic is harder than scalar arithmetic. So if everything in section 5 is a scalar, you can kind of go, oh, that feels better. Don't get too used to it. There'll be more vectors next week, but let's talk about the unit to measure work in. SI unit for force is a Newton. SI unit for displacement or distance, either one, is a meter. So work would be measured in newtons times meters. As is often the case, this combination of units is given a name of its own. It's named after James Prescott Joule. I won't bother telling you who he was. If you actually care, you know, that's why they invented Google. But he was this guy who lived in the 19th century, and they thought it would be a good idea to name this unit after him. That's the SI unit. The British, I guess I don't have that actually written down here anywhere, but in traditional British units, the equivalent would be to measure work in foot-pounds, and that does not have a name of its own. It's just a foot-pound. Some examples. So here's this little wagon, well, slightly further down the page is this little wagon I was talking about. Time to insert another book under the clipboard. A little further back. Okay, well, that's a rather steep angle to have the handle of that wagon at, but we'll just kind of go with it. So you pull that wagon 10 meters. The main thing I wanted to point out with this one is that you should not just go around oversimplifying things, saying to yourself, work equals force times distance, work equals force times distance. Because if that's all you think about, force times distance, then you are likely to look at this and say 20 Newton force, 10 meter distance, multiply them 200 joules. That's the wrong answer. There's also that cosine factor in there. So the correct answer it's the component of the force along the displacement times the distance, not the whole force times the distance. So you've got a 20 Newton force times the cosine of 60 degrees, which happens to be exactly 1/2, times the 10 meters. $100 joules, not 200. Next one, number 2. Carry this bucket of water 100 meters over level ground. How much work did you do? I always like to stop here and say, you know, well, what do you think? And if I'm lucky, somebody says 8,000 joules, and then I can make fun of them. But there's nobody here, so I guess I'll just have to tell you that the answer is 0. No work is done, at least not in this sense of the word. I mean, anybody who's ever carried water can tell you that's a lot of work, but not in this sense of the word, it isn't. So here's a little sketch of what's going on. There's the bucket. Can't draw human beings to save my life, but I have found I am actually pretty good at drawing buckets. It says you are walking along level ground, so the displacement. And again, this is not a force, okay? This is measured in meters, not newtons. This is the displacement, the movement, the change in its position for the bucket. And as you go walking along, the force you exert on its handle is that way. So notice that work has this cosine factor in it. And notice that these two vectors are perpendicular. The force has no component in the direction of motion. So since theta equals 90 degrees, since theta equals 90 degrees, the cosine of 90 degrees is 0, no work is done. Just to put a little more perspective on that, to kind of jump ahead a little bit into use a few words I haven't defined yet. Work is done whenever there's any kind of a transformation of energy, okay? As you pull the wagon down the driveway, chemical energy stored in your body that originally came from something you ate gets transformed into kinetic energy. And then the friction that makes the wagon stop again, if you let go of it, well, that takes, work done by friction amounts to kinetic energy being converted into thermal energy. It gets changed into heat. So work is done whenever, I guess one way of saying it is whenever you add or remove energy from an object. If you have a ball and you throw it, you do work on it, you're adding energy to it. And then friction may be, in the case of a ball, it hits the ground. Maybe a better example is if there's a book you don't like very much sitting on the ground and you kick it, okay? So by kicking it, you give it kinetic energy. You do work on it. And then as it slides across the floor, friction makes it stop again. The work done by friction converts the kinetic energy into heat. It takes energy away from the book and sends it somewhere else in a different form. So if theta is 0 through 89 degrees, so that the force has a component toward the front, it does positive work. Positive work means you're adding to the amount of energy this thing has, okay? If theta is 91 through 180 degrees, cosine of an angle in that range is negative. See, work is a scalar, but it can be positive or negative. Don't misinterpret any minus signs as being a direction. Scalars do not have a direction. Rather, positive or negative in this case basically means adding or subtracting. Are you adding to the amount of energy something has, or are you subtracting from the amount of energy it has? Okay, so a force that leans in the direction of motion, cosine is positive, that adds to the energy it has. A force that leans against the direction of motion will be taking energy away. That does negative work. If you're at 90 degrees, it does neither one. no work is done at all. So yeah, carrying a bucket of water makes you tired, but if you just stand in one place and hold a bucket of water for long enough, you'll get tired. All you're really doing with this bucket of water is holding it up so it doesn't rub against the ground, okay? Once you get the bucket of water, I mean, yes, you do a small amount of work at the beginning of the 100 meters to get the bucket moving in the first place. But once it's moving at a constant speed, it continues to move just because of Newton's first law. All you're doing is holding it up to keep it off the ground so it doesn't rub and there's no friction. When you get to the other end of the 100 meters, there'll be a small amount of negative work as you stop the thing again. But during that time in between, while you're just moving at a steady speed, no work is done. Number 3. The first 2 questions were about the work done by a particular force. In number 3, by the time we get to the last part, we're finding the total work done on an object by all the forces that act on it. But the first couple parts amount to finding the work done by one force at a time. So I will escort you back over to this end of the table here. Number 3. Part A. The work done by the rope. You know, since you can't quite see the handout right now, maybe I'll make a quick little sketch. Same picture that's on the handout. But you've got, I called it R for rope, 20 newtons, and you've got friction pulling the other way, and that's 5 newtons. And if I was doing a really complete picture, there would be the normal force and the weight also. That's all the forces that act on this block. So in part A, the 20 Newton force that I called R points that way. The block is being dragged to the right, so the displacement vector also points that way. If you were to stick these 2 arrows together, they make a 0-degree angle. So the work done by this force is 20 Newton force. Well, magnitude of the force really is the right way to say it. 10-meter displacement. Cosine of 0 degrees is 1. That force does 200 joules of work. A Newton times a meter is called a joule. Part B. The work done by friction. Friction force points that way. The displacement is the same displacement that I was talking about in part A. You stick these 2 together, they make a 180-degree angle. So we've got 5 newtons for the force of friction. Once again, the block goes 10 meters. Cosine of 180 degrees is -1. And maybe I should pause here for a moment just to make a general point. Remember the catchy little phrase, Friction always opposes motion. No matter what direction something is moving in, the force of friction always makes a 180-degree angle with the direction that the thing moves. So if you're going to calculate work done by a friction force, the cosine factor is always -1 for friction. So minus the force times the distance is going to be the force, or the work done by friction. So you multiply this out and it's 50 or -50 joules. Now the question doesn't ask for the work done by the weight or the normal force, but if it did, it would be just like the example with the bucket, okay? They act perpendicular to the direction of motion. So the work done by both of those is 0. Total, just add up the work done by the individual forces. You've got a positive 200 and a negative 50, 150 joules. Or an alternate way of looking at it that would get you the same answer, the total work would be the work done by the total force. If you've got 20 to the right and 5 to the left, that's a net force of 15. 15 newtons times 10 meters takes you to the same answer. Okay, the next thing on the list here is just the phrase kinetic energy underlined. So I'll shift you over a little bit and introduce the idea of kinetic energy. Work and kinetic energy. A few lines of math that will lead to a useful result. We're going to start with Newton's second law. Maybe I should make a little sketch so you've got something specific in mind for what I might be talking about. This might be the glider on the air track from the F = ma lab, okay? The air track created a more or less frictionless surface. There was that little strap, the old piece of audio tape that pulled on the glider, and that's creating this force here. And let's consider the glider moving some distance. Well, let's call it some displacement, delta x. Okay, so if you want something specific in mind, think about that. I'm going to apply F = ma to that. I'm going to substitute in the definition of acceleration. Delta v over delta t, with the understanding that if the force changes as time passes, you'll need to take the limit as delta t approaches 0. Okay, so delta t might be infinitesimal if you need to do that, but that's the acceleration. Also, I'm going to multiply both sides of this equation by the displacement, how delta x, how far does the glider move? Something that might also be infinitesimal if you decide you need to take a limit. The reason I did that is because the force times the displacement would be the work done. In this case, the cosine factor would equal 1. I'm sort of looking at a special case here to keep the derivation simple. You can make a more generalized version of the same argument where the force might be in some sort of an angle, but let's keep it simple and assume that, it's a glider going down a horizontal air track being pulled by a horizontal force. So force times displacement work. Over here on the other side, I'm just going to rearrange a few things. Recopy the M, recopy the delta V, and I'm going to take the delta T and slide it over so it's underneath the delta X. Like that. If you refer back to section 1, displacement over time is the average velocity. If you refer back to section 1, something else that's equal to average velocity is 1/2 that's a formula from section 1. V average equals 1/2 V final plus V initial. If you're watching a car, steadily gains speed. If it starts out at 20 miles an hour, ends up at 40 miles an hour, the average velocity is in the middle, 30 miles an hour. Hopefully that sounds familiar. I'm going to stick the 1/2 over here in front of everything else. Delta V, of course, means V final minus V initial. So instead of just writing delta V, I'll write that out. And then recopy the V final plus V initial. And then hopefully you remember how to factor the difference between two squares. From algebra class, if you've got a squared minus b squared, that's equal to the quantity a minus b times the quantity a plus b. If you don't remember that, I just told you. It's exactly what we have here. So I'm going to distribute the 1/2 m across both of those terms. And that means we have work equals 1/2 mv final squared minus 1/2 mv initial squared. So I have just shown that An object can do work by changing the amount of 1/2 mv squared it has. That makes 1/2 mv squared sound like it's stored up work, okay? Something like that probably ought to have a name of its own. What do you say we call it kinetic energy? That's kind of a catchy sounding name, don't you think? Define kinetic energy. Shall abbreviate KE. This, by the way, is one of those formulas I did not put on the formula sheet. It's not a terribly long, complicated formula, and it's fairly central to the subject, kind of like F equals MA. F equals MA is not on the formula sheet. You're supposed to know it. And so be sure you know that, or you may come to grief. Unit to measure, well, not only kinetic energy, but any kind of energy is measured in units of work. In the SI system, joules. In customary units, foot-pounds. Again, well, actually, let me make this substitution. This is the final kinetic energy. This is the initial kinetic energy. So, summarize, get to the part with the box around it. I have just demonstrated that the work done on an object equals the change in its kinetic energy, which is one form of something called the work energy theorem. Work energy theorem. So if the amount of, you have to do, what this says is you have to do work on an object to increase the amount of kinetic energy it has. And the object can do work for you by decreasing the amount of kinetic energy it has. So kinetic energy amounts to stored up work. Turns out not to be the only way of storing up work. We'll see as we go along that there are other types of energy also, but that's what it all means. So before I go any further, a couple of examples actually. I think I'll go through both of these and then maybe that's the point where I'll break off, come back in a second recording for the rest of section 5. Focus, please. Come on. Sometimes that helps. This was not one of those times. Closer. No. Well, you can read it even if it's not the best I've ever seen. Actually, I guess I need to raise it up, don't I? Oh, and for some reason that made it get clear. Okay, so number 4, to illustrate the idea that energy is stored up work, let's create a situation where there is something for the work to be done on. Let's say your mass is 70 kilograms. Let's say you're riding in a car that's 20 meters per second is roughly 45 miles an hour. And well, let's just get that part taken care of and then we'll come back. Part A is just calculate your kinetic energy. is just dropping numbers in the formula, really. No, I didn't want to do that. I want to get playing with the camera again. Sure hope chalk dust isn't bad for that thing because I'm getting fingerprints all over it. Anyhow, there it is. Couldn't figure out where I set that down. Part A. Energy equals 1/2 mv squared. Your mass is 70 kilograms. Your speed is 20 meters per second. And this is pretty much just a plug and chug calculation. 14,000 joules. That's how much kinetic energy this person has as they go down the road at this speed. So now, to illustrate the idea that kinetic energy means stored up work, let's give you something to do the work on. Part B says that apparently the driver was playing with their phone or something like that. The car stops rather abruptly when it hits, you know, like a 500-year-old tree or something like that. And so the airbag makes your speed go from 20 meters per second to 0 as you move through a distance of 1/2 meter. And it says how much, well, find the average force, okay? The way I'm going to do it is from the change in your kinetic energy, you can find how much work was done. If work is equal to force times distance, and you know the distance, you can find the force. That's the summary of the thing. As far as nitpicky details, there's always some minus sign somewhere that has to be explained. So let's say, oh, I don't know, let's say you're going that way. So here's the airbag. And this is you. One of those spherical people. So the direction of your displacement, you know, the direction that the car is moving, let's say it's that way. As you collide with this airbag, it's pushing on you in that direction. The airbag exerts a force on you that opposes your motion and brings you to rest, okay? So if the displacement is that way and the force is that way, well, actually, I should really draw it the other way around. Point of all of this is the force and the displacement have opposite directions. So when we go to calculate work, theta is 180 degrees. In this case, it's not a friction force, but it's the same as friction in the sense that it points exactly the opposite way from what you're moving. So the work will be minus the force, you know, minus F times S. Work energy theorem. Work equals the change in your kinetic energy work by definition is F cosine theta times S. Change in kinetic energy means kinetic energy final minus kinetic energy initial. Delta anything is final minus initial. Force is the unknown that I want. As I explained over here, the cosine factor is equal to -1, cosine of 180 degrees. Distance is 1/2 meter. The final kinetic energy is 0 because in the end you stop. And the initial kinetic energy, that was the answer to part A, 14,000. The minus signs cancel each other. If you multiply through by -1, they're gone. Which means in this particular case, you would have got away with it if you missed them both in the first place, if you didn't stop to think that the work would be negative, and you didn't stop to think that the kinetic energy was decreasing. Yeah, remember when your mother told you 2 wrongs don't make a right? You listened to your mother? Actually, most of the time. Sometimes I listened to my mother, but at least in algebra, sometimes 2 wrongs do make a right. If you miss 2 minus signs, it balances out. Solving for the force, we've got 14,000. Oh, I might as well stick the units on there and show you how they work. Remember, a joule is equivalent to a Newton times a meter. And that gets divided by 0.5 of a meter. So meters over meters cancels out, and the force comes out in newtons as it should, 28,000 of them. Roughly 6,300 pounds, so approximately 3 tons. Now, nobody promised that you weren't going to get out of this accident with a few bruises, without a few bruises at least, but consider the alternative. And the physics point that I'm making here is that energy means stored up work, not stored up force, okay? There is no particular amount of force associated with having 14,000 joules of kinetic energy. It all depends, the force all depends on the distance. If you're riding in some old car that doesn't have airbags or even seatbelts, and instead of stopping in 1/2 meter by running into this airbag, let's say this is 0.05 of a meter, which is perhaps the distance that you would move while the windshield and your skull get smashed up. Well, if that distance gets 10 times smaller, this force gets 10 times bigger, and now you're talking about 30 tons instead of 3. Plus, really, injury depends more on pressure than total force. And if you go into the windshield, the force is distributed over a much smaller area than if you land on this large pillow-like object, okay? So you not only have 10 times as much force, it's distributed over a much smaller area, which creates considerably more pressure. So that's why the airbag is better. I mean, three tons is not something you want briefly acting on you, but imagine going to the other extreme just for one more illustration. If you were going along at 45 miles an hour and somehow manage to land in an enormous pile of shaving cream, that instead of stopping you in half a meter, if it stopped you in 5 meters instead, then that would be even more gentle. It would be only, take that 0 off of there, it would be only 2,800 newtons instead of 28,000. So no particular amount of force associated with having this much energy, but it always works out to this much work being done. Big force times a little distance, or a little force times a big distance. Either way, that's the amount of work it would take to stop you. One more example. Break this off. Why, I think what did I do? I think the cord brushed across something on the computer. Okay. Example number 5, which is once again all fuzzy and hard to read. Oh, and there it is. Sometimes I really wish this just had a manual focus. Number 5 involves a lot of the same ideas as number 4. In a way, it's kind of a similar question, but it's 2-dimensional instead of 1-dimensional. You've got an object moving in a plane rather than just moving along a line. So find the work done on it. Once again, like the one I just did, I'll find the work by finding the change in kinetic energy. Okay, I'll calculate the final kinetic energy, I'll calculate the initial kinetic energy, and then the difference between them will be the answer, because the work energy theorem says so. Okay. Back again. Apparently that wasn't a cord brushing against something on the laptop. Apparently the camera is a little loose in its base. I stuck it down in there better, and maybe now I can do that again. Number 5. So the strategy is to find the work from W equals change in kinetic energy. Kinetic energy initial would be 1/2 the mass times the initial velocity squared. And the initial velocity is given in the question, but we now have to confront the issue of how do you square a vector? Well, there's a couple of ways of explaining it. I mean, what it kind of comes down to is to square something means to multiply it by itself. In this case, multiply means the dot product. It'll be v dot v is what v squared is. But if you want to think in terms of pictures instead of, abstract operations that you didn't hear of before today, pictures go like this. There's an arrow whose length is vi. That would be the initial velocity. It has an x component, vix, and a y component, viy. These are related to each other by the Pythagorean theorem. The x and y components are given in the question. The initial velocity has an x component of, let's see which one is which here. Yeah, t equals 2 seconds and t equals 5 seconds. The only thing that those numbers are good for is it tells you which one is initial and which one is final. The fact that it's 3 seconds in between has no effect on the answer. But the initial velocity would be the one at t equals 2 seconds. So we've got an x component of 12 and a y component of 6, and you can stick those in there, and that'll give you what you need to put in for v squared. Or another way of explaining it, like I mentioned a moment ago, I should have mentioned, by the way, when I first introduced the dot product at the beginning of this video, that, where do I have that in here anyhow? There's somewhere in the formula sheet, it tells you how to do these vector products. Okay, the dot product is tucked away under section 5. And I don't know if you can read that. There we go. Dot product. The way you do a dot product with the components is you multiply the x components together and you multiply the y components together, z components if it's a three-dimensional problem, and then you add. So using that, v dot v, if you're multiplying something by itself, then you would, what that calls ax times bx. Well, a and b are the same vector in this case. That would be the x component squared. And likewise, ay times by, again, a and b are the same vector, so that would be the y component squared. So you can look at it this way, or you can look at it this way. Either way, that's how you square the vector. Let's throw the numbers at it. We've got mass, 3 kilograms. X is 12. Y is 6. Okay, so V initial squared, X component squared plus Y component squared. This would then be meters squared per second squared as far as the units go, times kilograms. If you break it all the way down to base units, that's what a joule is. Units of mass times velocity squared. Kilogram, meter squared per second squared. $270. Same thing over again to get the final kinetic energy. Mass is 3 kilograms. Components of the final velocity. It's going slower now, and so it doesn't have as much kinetic energy. Work, according to the work energy theorem, work is equal to the change in the kinetic energy. Delta anything is always final minus initial. It doesn't mean subtract in whatever order makes it positive. It means final minus initial, which in this case is 30 minus 270, which comes out, I guess I'm going to shift over to here. negative 240 joules. And as I've already explained a few times, but maybe phrasing it a little differently, the minus sign means work is being done by the object. Work is done, if work is done on the object, then the work would be positive. If work is being done by the object, then the work is negative. On the object, meaning energy is being added to it. In this case, energy is being lost. With any kind of a change, gains are positive, losses are negative. Okay, in our next exciting video, I will introduce the idea of potential energy. Bet you can't wait.